Hello, welcome to this video telling a brief history of ecological economic modeling. Let me start with the question, what is a model? After a paper by Baumgärtner et al. In 2008, a model is an abstract representation of a real system. Abstraction is something we do all the time. For example, when we look for a chair, we usually only observe its general shape so that we don't miss the seating area when sitting down. But we do not observe all the details, such as whether the chair has been glued or screwed. Here we trust the manufacturer that the chair is solid. In this manner, we are all modelers. Later on in Baumgärtner et al., we learn that models are constructed for a specific purpose. Such a purpose can be to gain a better understanding of the focal system, or to predict the system's future, or simply to communicate information. Here a model of the university campus in Cottbus that helps me finding my way to the lecture room. Models have been used by humans for thousands of years. In the ancient times, for example, people felt a strong need to understand the world and their own role in it. So they constructed models of their world that also helped in organizing their life, such as the timing of cropping over the year. Soon, however, the earliest world models that placed Earth into the center of the universe were observed to conflict with, or at least be suboptimal for explaining, real-world observations, such as the movement of cosmic bodies. And so in the Middle Ages, Copernicus and others decided it might be more adequate to assume the Sun as the center of the solar system. Copernicus too, however, still believed in the divineness of continuous movements and the perfect symmetry of the circle. So he assumed that the planets, including Earth, would revolve around the Sun in circles. With the ever-improving optical instruments at these times, Copernicus's world model too got into conflict with real-world observations, for example those by Galileo, a conflict that was resolved by Johannes Kepler's model, which considers that the planets move on elliptical paths. Nowadays we know that even this is not perfectly correct. Instead, the ellipses are not closed, but the planets' trajectories have the shape of a rosette, which about 100 years ago was used as a confirmation of Einstein's general theory of relativity. Until the 17th century, models had been mostly of a verbal or geometric nature. This changes during the time of the Enlightenment, when science undergoes a dramatic progress. A most prominent step in this process is the unification of physics, in particular mechanics, and mathematics. And one of the main protagonists here is Isaac Newton, next to Gottfried Wilhelm Leibniz, with whom Newton quarreled about the ownership of numerous revolutionary ideas till the end of his life. But the theory of motion, nowadays taught at universities as classical mechanics, is clearly to the merit of Newton. For his theory of motion, Newton combined three contemporary theories: Galileo's theory of acceleration, Kepler's already mentioned theory of the planet's motion, and Descartes' law of inertia, now known as Newton's first axiom. And he combined these with a new developed mathematics, in particular calculus. This resulted in Newton's equation of motion, that force equals mass times acceleration, meaning, for instance, that a higher force provokes a higher acceleration of the affected body, or that a light body is, by a given force, accelerated more strongly than a heavy body. where acceleration is the time derivative of velocity and velocity is the time derivative of the traveled distance. Or equivalently, velocity is the time integral of acceleration and the traveled distance is the time integral of velocity. This theory was then successfully applied to describe the planet's motions in the solar system by adding a model for the force between Sun and planet. In this model, Newton assumed that the force is proportional to the product of the Sun's and the planet's masses divided by the squared distance between Sun and planet and multiplied by the proportionality factor gamma, which is the so-called gravitational constant. The magnitude of this gravitational constant was approximated by comparing model predictions with real observations, and later estimated with much higher precision in physical experiments. This enormous success of mechanics spurred a firework of ideas in the following centuries, up to the assumption that human bodies would consist of mechanical machines with cogwheels inside. So it is no wonder that economists about 100 years later adopted a number of concepts from Newton's mechanics. One of these is the concept of optimality, which in physics tells us that closed systems, these are systems that do not exchange matter or energy with their environment, eventually develop into a state of maximum entropy, or implied by this, a state of minimum free energy. In economics, Adam Smith, the father of modern economics, proposed that the benefit striving of the individual people would maximize the welfare of society as a whole, and that the people's interactions in the perfect market would optimize the allocation of resources, goods, and services. Then, in physics, we have the concept of equilibrium. For example, if there is a balance of forces, acceleration will be zero and physical bodies either rest or move at constant speed. In economics, Léon Walras introduced the concept of market equilibrium in which goods are allocated constant and optimally. And as a third example, economists adopted the method of calculus and differential equations. An example of such a differential equation we have already seen if we consider that acceleration is the second derivative of the traveled distance with respect to time. So the shown differential equation describes how the location of the physical body changes in time if it is subjected to the force F. Analogously, Thomas Malthus described the growth dynamics of the human population by a differential equation in which the rate of population change, dn over dt, is given by the population size n multiplied with the per capita population growth rate r. Solving this differential equation, we obtain that the population size will grow exponentially over time. Next to this, Malthus assumed that the rate of change of available resources would only be constant, implying a linear growth of the resource over time. From which Malthus concluded that humanity would run into a crisis of starvation and death. Today we know that Malthus was, fortunately, wrong by underestimating technological progress, which allows for overlinear growth of the available resources. So one should not exclude that in the future we will run into shortage of some resources, but the socio-environmental system is way too complex to predict precisely the occurrence of such shortages as well as their consequences. In biology, mathematical models play only a minor role before the 20th century. Although there is a number of other groundbreaking developments in the field, such as taxonomy by Carl von Linné, the theory of evolution by Charles Darwin, and the science of inheritance by Gregor Mendel. An important example of mathematical modeling, however, should be noted, which is the logistic growth model by Pierre-François Verhulst. It challenges the assumption of indefinite growth in Malthus' model and instead proposes that, due to limited resources, the per capita population growth rate R is not constant but declines as the population size N increases and the per capita share of the resource declines. As the simplest model, Verhulst assumed that the growth rate would be maximal for very small population sizes and decline linearly with increasing population size. If the population size reaches the carrying capacity K, which measures the amount of available resources, the growth rate is zero, and for population sizes above K, it even becomes negative. The consequences of this model extension are quite straightforward but insightful. For population sizes below the carrying capacity, the growth rate is positive, and whatever the current population size, the population will grow. However, the larger the population, the slower the growth, so the population keeps growing but at a decreasing rate, and over time asymptotically approaches the size of the carrying capacity. The opposite happens if we start from a large population above the carrying capacity. For large deviations, we observe a fast decline, which however diminishes over time, and the population asymptotically approaches the size of the carrying capacity from above. Since any population size will eventually lead into a population with the size of the carrying capacity, that state at which the population is at the carrying capacity is a stable state, so that after any disturbance that might have moved the population up or down, the population will return just to the carrying capacity. In the 20th century, the world becomes complex. The classical thinking, assuming linearity, determinism, and equilibria, increasingly reaches its limits, meaning that the existing theories and models cannot reasonably describe nor explain observed real-world phenomena. Let me present a popular example from physics, the three-body problem. To introduce this problem, first consider a simple three-body problem: Sun, Earth, and Jupiter. There are three bodies in the system, but the mass of Jupiter is small compared to that of the Sun. And since Jupiter is far away, we essentially have a two-body problem with Sun and Earth, not interfered by Jupiter. And actually a second two-body problem with Sun and Jupiter, not interfered by Earth. So the movement of Earth has the well-known circular, or precisely elliptic, shape. Now let us increase Jupiter's mass to 10% of the Sun's mass. We still find Earth roughly in its familiar distance to the Sun, but its movement is much less regular now, with constantly changing radii within certain bounds. We would still speak of a stable system, but life on Earth would probably be slightly uncomfortable. If we further increase Jupiter's mass to half the Sun's mass, Earth's distance to the Sun is becoming even more variable. In fact, the trajectory has become totally irregular, or chaotic, as we say. This is the essential property of three-body systems, that they show chaotic behavior. For even larger Jupiter masses, chaos gets so severe that Earth leaves the Sun's domain of attraction and gets caught by Jupiter, or even gets kicked out of the solar system altogether. In ecology, we can observe chaotic dynamics as well. Reconsider the logistic growth equation I had introduced above. The only difference is that now we consider discrete time steps rather than continuous time. The graph shows the population size over time for a starting population half the size of the carrying capacity, with a growth rate of R equal to 3. we can see that the dynamics are bound between 0 and 1.5 times k, but are quite irregular, chaotic, in the sense that it is not easy to guess the future of the population even in the medium run. A typical characteristic of chaotic systems is that their dynamics in the long run very sensitively depend on the initial condition. If we increase the initial population size only by 10 to the minus 5 in units of the carrying capacity, here shown by the red line, in the beginning it seems this has no effect, but after about 10 time steps, we start to see small deviations to the blue line, and after another 5 to 10 time steps, the two trajectories are totally different from each other. So chaotic systems are in principle predictable, that is, described by deterministic equations, which distinguishes them from stochastic systems. But since initial conditions can in practice never be measured with perfect accuracy, in practice, chaotic systems are, at least in the long run, unpredictable. Somewhat critical or disappointed, one must say that over much of the 20th century, all these exciting developments in the natural sciences are not recognized by most economists who adhere to the worldview of classical mechanics with its concepts of linearity, regularity, and equilibrium. At least, economists increasingly acknowledge already at the beginning of the 20th century that humans' economic activity is not without bounds and must be fenced by appropriate policy instruments, such as taxes on resource use or environmental pollution. Still, the optimization of these policy instruments largely relies on assumptions of stationarity or even constancy and determinism. In the 1980s, a new concept emerges which will also influence various economists. Resilience, which is the capacity of a system to absorb disturbance and reorganize while undergoing change, so as to still retain essentially the same function, structure, identity, and feedbacks. There are two major types of processes that characterize the resilience of a system. For the first, consider the system metaphorically as a ball that lies on the bottom of a trough. If the ball is moved to the left or to the right, it will eventually return to its original position. However, if the disturbance is too large, the ball will cross the barrier and roll into the other trough to the right, representing a qualitative change of the system. Alternatively, next to a large disturbance, the resilience of the system may be reduced if the resilience landscape is changed and the barrier between the two troughs is reduced. Then even a small disturbance is able to tip the system from the left state to the right. In the following, I will demonstrate these concepts on a simple ecological population model. The model considers the case of the highly endangered orange-bellied parrot in Australia. The bird breeds in the southwest of Tasmania and migrates to the Australian mainland to overwinter in the coastal salt marshes of Victoria and South Australia. In the past, the population size has dramatically declined. In the 1990s, it appeared stable at rather low numbers, but today there are only about 20 individuals left. The main reasons for this decline are loss of wintering habitat, fatalities during the migration between Tasmania and the mainland, and the alley effect. What is an alley effect? To understand the alley effect, reconsider the logistic growth model. As explained on one of the previous slides, for population sizes below the carrying capacity, we have positive growth towards the carrying capacity, while for population sizes above the carrying capacity, we have negative growth towards the carrying capacity. So the state where the population is at the carrying capacity is stable. After deviation from that state, the population always returns, as in the metaphor of the ball in the trough. For many species, including the orange-bellied parrot, this population growth model is overly optimistic for small population sizes. At small population sizes, individuals often suffer increased mortality, for example from predation, and it is often difficult to find a mate, not to speak of inbreeding depression. So in many populations, the growth rate does not keep increasing if the population size is reduced, but at some point it declines and can even become negative for very small population sizes. This region of negative growth is very critical because once the population falls below the alley threshold at which the growth turns from positive to negative, it will keep declining to zero with no chance of returning to larger sizes. Thus, above the alley threshold, the positive growth drives the population to larger numbers, while below, the negative growth drives it toward extinction. So the state where the population is at the alley threshold is unstable. What can we conclude from this model? An extinction of the population is possible, but it can be prevented as long as the population size is maintained above the alley threshold. This is, of course, again over-optimistic. We, as well as the orange-bellied parrot, do not live in a deterministic world, but are affected by unpredictable events, which include catastrophes. For the parrot, these catastrophes come in the form of storms during the migration phases between Tasmania and the mainland, which can easily kill a large portion of the population. These catastrophes can be regarded as disturbances that keep pushing the population away from its stable state at the carrying capacity. As we saw with the metaphorical resilience model, as long as the disturbance is not too large, the system, in the present case the parrot population, can always return to its stable state near the carrying capacity. But if the disturbances are too large, they can push the population beyond the LA threshold into a domain of small population sizes from which it cannot escape and eventually goes extinct. Within the framework of the resilience concept, the disturbance has tipped the population over the barrier formed by the alley threshold into the state of extinction. Now let's model this process mathematically. We start from the logistic growth equation, whose shape is determined by the intrinsic growth rate Rm and the carrying capacity K. Please note that the numerical values of these two parameters were chosen for the purpose of demonstration rather than to describe the real situation. Now we add the alley effect so that for decreasing population sizes, the growth rate declines. This decline is described by a slope b and the intercept a, which formally gives the growth rate at zero population size. Lastly, we add the catastrophes. In each simulation year, a random number is drawn from the uniform distribution with bounds of 0 and 1 and multiplied with the current population size and a catastrophe factor k. And the product is subtracted from the current population size. By this, in each simulation year, a random proportion between 0 and k is taken out of the population. And here we see the simulation results, starting from a population with initially k equal to 150 individuals. The graph shows the probability distribution of the population size after 1 year. As one could expect from the catastrophe model with k equal to 0.2, all population sizes between 150 and 150 times 0.8 are equally likely. After 10 years, the probability distribution is peaked around some most likely population size around 90. Extinction, that is zero population size, does never occur until that time step. This is found even after 50 years. Although the distribution has shifted slightly to smaller population sizes, it remains at strictly positive population sizes, and population extinction can be excluded. The reason is that the catastrophes are unable to tip the population into the state of very small population sizes at which extinction becomes inevitable. What happens if we raise the strength of the catastrophes to k equal to 0.25? After the first year, we observe, as expected, a similar result as for k equal to 0.2. And even after 10 years, the situation looks quite similar to the result for k equal to 0.2. But after 50 years, we see that the probability of observing small population sizes below the Ellie threshold has dramatically increased. So the stronger catastrophes are able to tip, in the long run, the population into the state of extinction. This represents the first way of affecting the resilience of a system. For the second way, changing the resilience landscape, let us maintain the current strength of the catastrophes, but introduce conservation measures that double the carrying capacity from 150 to 300. The result can be seen here. The resilience landscape looks, on first sight, similar, but notice the doubling of the scale of the horizontal axis, so that the trough to the right of the barrier, which corresponds to the size of the carrying capacity, is now much further away from the barrier. As we can see, the catastrophes are not able to tip the population into the state of extinction. I have actually continued the simulation for several hundred years, and the population always survived. Now turn to a second important concept established in the 1980s, sustainability. Very roughly, one may say it is the resilience concept plus the normative choice that some system states are preferred to others. For example, that a world with orange-bellied parrots is, all other things equal, preferred to a world without orange-bellied parrots. A typical problem of sustainability is how to manage natural resources so they can persist. As a very simple example, let us interpret the parrot population as a fish stock and the catastrophe strength K as a harvesting rate. A central question in the sustainable management of natural resources is, by how much can we harvest the resource? Our model tells us that for a carrying capacity of 150, this maximum rate is around 0.2. Of course, one should not take this number too literally. For a reasonable estimate, this demonstration model is far too simple, and much more sophisticated models exist to answer such questions. Now we have reached the final part of this presentation, which is about ecological economic modeling to integrate ecological models, like the parrot model, with economic models and data. These models have an ecological and an economic component and an interface component that links the two. Ecological economic models are, compared to disciplinary ecological or economic models, particularly useful if recommendations for the design of biodiversity conservation policies from the respective disciplinary models are not compatible with each other, or there are feedbacks between the ecological and the economic system components. Now I want to show an example of such a feedback loop in an ecological economic model. The model is used to compare output-based payments with input-based payments for the conservation of a mobile species. Conservation payments are economic instruments to induce landowners to conservation activities. In input-based, or also called action-based payments, landowners receive a payment if they carry out particular conservation measures. Output-based or results-based payments are offered if a particular conservation objective, such as the presence of a species on the land, is achieved. An advantage of output-based payments is that the conservation agency pays exactly for the desired good, the presence of the species, rather than for a proxy, the conservation measure, so at least in theory, output-based payments are by design cost-effective. A disadvantage of output-based payments is that the achievement of the ecological objective is only partly in the landowner's control and is, instead, also influenced by random factors such as weather or the dispersal behavior of the species. As a consequence of this uncertainty, landowners will demand, in addition to compensation for their foregone profits, a risk premium which raises the cost of the payment scheme to the conservation agency. In the following, I want to explore the dynamics of output-based payments with a generic ecological-economic model. The main features of the model are: the conservation agency offers a payment to the landowners. A landowner carries out the conservation measure if and only if the payment exceeds the landowner's foregone profits plus the risk premium. If the conservation measure is carried out on a land parcel, neighboring local populations of the species may, with a certain probability, colonize this land parcel. On unconserved, economically used land parcels, local populations go extinct with certainty. On conserved land parcels, they go extinct with a certain probability. For the calculation of the risk premium, the landowner observes the number of neighboring local species populations and calculates the probability that his or her land will be colonized by the species. This, in fact, forms the feedback from the ecological into the economic system component. In the following, I will show you a typical simulation of the coupled ecological-economic dynamics induced by the output-based payment. The model is implemented in NetLogo. Initially, we see an agricultural landscape with black land parcels and a few permanent reserves occupied by the species in yellow. After the first time step, some land parcels adjacent to the reserves where the local populations have turned to conservational use in green color, because this choice is expected to be more profitable than agricultural use. Some of the conserved land parcels are colonized by the species and harbor a local population in red color. After the second time step, some more agricultural land parcels have turned to conservational use. A few local populations have gone extinct, indicated by a change from red to green color, while a few conserved land parcels have been colonized, now in red color. Here we see the dynamics over a number of time steps, with changing proportion of conserved land parcels in green color and proportion of occupied land parcels in red color. To summarize and better understand the dynamics, let us have a look at the phase diagram. A phase diagram depicts the state of the system and the changes of that state over time in the coordinates of the important state variables. In our case, these two state variables are the proportion of conserved land parcels, measured on the horizontal axis, and the proportion of land parcels occupied by the species, measured on the vertical axis. Each point in the phase space represents a mathematically possible state of the system. Here, for numerical reasons, the two states were grouped into intervals, represented by the squares. So the marked square, for example, summarizes all states with proportion of conserved land parcels between 10 and 15% and proportion of occupied land parcels between 15 and 20%. The gray shaded squares represent the states that are actually assumed in the course of the system dynamics. One can, not unsurprising, see a strong positive correlation between the two state variables, so that small proportions of conserved land parcels coincide with rather small proportions of occupied land parcels, and large proportions of conserved land parcels coincide with rather large proportions of occupied land parcels. The arrows in the graph indicate the most likely transitions between different states. More likely transitions are shown by darker color. In the upper part of the gray area, where the proportion of occupied land parcels for a given proportion of conserved land parcels is above average, we see arrows pointing upwards, to the right and towards the upper right, so the system moves to more conserved land. The reason is that if many land parcels are occupied, it is likely that a particular conserved land parcel will become occupied too, so its landowner will receive the payment and conservation is profitable. So an increasing number of landowners will conserve their land. This expansion of conservation, in turn, implies an increase in the proportion of occupied land parcels, which in turn renders conservation even more profitable. So the system moves to the upper right, that is, to more conservation and more occupied land parcels. However, the ecological dynamics involve stochasticities in the colonization and extinction events. In a sequence of bad years, the population may decline and land parcels become empty, despite a large proportion of them being conserved. In the phase diagram, this is represented by a downward move. This again has consequences for the landowner's decisions, because it is now less likely for a conserved land parcel to become occupied and conservation becomes less profitable. So some landowners will convert the land back to agricultural use, which reduces the proportion of conserved land parcels and eventually also the proportion of occupied land parcels. So the system moves to the lower left. Only by a sequence of good years can the population increase again and occupy more land parcels. And the landowners will respond with conserving more land parcels, and the cycle starts anew. This feedback loop has consequences. When considering only the long-term average of the system state variables, not considering their oscillations induced by the feedbacks, the output-based payment is generally more cost-effective than the input-based payment. But if we also consider the temporal variability in the proportions of conserved and occupied land parcels, then we find for moderate ecological targets, with respect to the proportion of occupied land parcels, and generous conservation budgets, that the input-based payment is more cost-effective than the output-based payment. Such a result could, quite clearly, not be obtained by disciplinary ecological or economic models. So I hope I could demonstrate the added value of ecological economic modeling in the analysis of input and output-based payments. Such an added value can, of course, also be achieved with many other coupled ecological economic systems. And with this final conclusion, I want to end my presentation and thank you for your attention. I hope you enjoyed the talk and got something useful out of it. And if you have questions or comments, please don't hesitate to contact me.